Let's get started. Is this compound R or S? Pregabalin, epileptic drug. Carbon right here. Is it R or S? Anybody get this? Anybody?
S.
Yes. There's an H here. It's going back. That's going to be low priority group because the others are carbon. What's carbon, carbon, or carbon? Well, you have to look what's attached to the carbon. This carbon is attached to what? An N, H, and an H. This carbon is attached to what? Carbon, H, and an H. This carbon is attached to what? Carbon, H, and H. You look at the first, you look like this. What wins out, nitrogen or carbon? Nitrogen. So this is going to be high priority group. This is going to be 1. So this is 1. Okay, 2. Is it carbon or carbon? Well, what's it attached to? It's attached to these. Those are the same, so you got to look at one more. This carbon is attached to what? O, O, and O. The double bond to O is like it's attached to 2 O's. Where this carbon is attached to what? C, C, and H. C, C, and H. Look at the first one, what wins out? Oxygen or carbon? Oxygen. So this is 2, this is 3, or we can say that's 2, this is 3. H in the back, 1, 2, 3, going counterclockwise. This is S. S. The configuration is S. Is the drug D or L? Anybody? The answer is we have no way to tell. You got to know the rotation, unless you're given that. There's no way to tell from the information given. I have no idea.
Wouldn't there be another chiral carbon in the carboxylic acid?
What's chiral?
The carbon in the carboxylic acid.
No, that's trigonal planar.
Okay.
Planar carbon is not chiral.
Oh yeah, I didn't think about the double bond to oxygen.
Okay. Did I just erase? Okay. Dang it. Boom, boom, boom. Okay, we had these here. What was this? Bold. And this was. This was bold and dash. Is that right? This was dashed, and this was bold. This was dashed and dashed. Okay, you already have those numbered, 1, 2, 3, 4. R or S here. Oxygen 1. Carbon with chlorine is going to be 2. This carbon only has H's, so it's 1, 2, 3. H here is in the back, so it's what? R. Okay. Carbon here. H is in the back. Chlorine 1. Carbon with oxygen 2. Carbon with just H's is 3. 1, 2, 3. What is this? Also R? Yes. So what is this? RS, SR, and SS. Okay. So once we know this, if the backbone's the same, we know that that's the same thing, right? But here we switch it to S. Yeah? Everybody have these? Okay, 1, 2, 3, 4. How many stereoisomers are possible for the following compound? 4. And here they are. How do we get 4? To determine the possible number of stereoisomers, it is n to the 2 power. No, that's not it. N to the 2 power.
2 to the n.
Be 2 to the n power. Let's see if that's right. 2 to the n power. Yeah, it's got to be this. 2 to the n power, where n is number of stereogenic centers or sites. The compound we're looking at has 2 chiral carbons. A chiral carbon is an example of a stereogenic site or stereogenic center. Because at that center you have stereochemistry that's been produced because of the arrangement here. 2. 2 stereogenic centers, 2 to the 2 is what? 4. Okay? What if there were 3 chiral carbons? How many stereoisomers would you? 2 to 3 would be 8. What if you had 9 chiral carbons? Yeah, you need a calculator. Okay? Now this is the max. This is the maximum number. We can have less. And we will talk about that. We can have less. Stereogenic sites, a chiral carbon. An alkene, though, is also a stereogenic site, potentially. Not all alkenes. But aren't some alkenes stereogenic? Some alkenes can be E or Z. Okay, so here are the 4. We can draw these. What's the relationship between the 4? They all can't be mirror images of each other because one thing only has one mirror image. What's the mirror image of number 1?
Number 4?
Yes. These here are, what's the relationship between these 2? Enantiomers. 1 and 4 are enantiomers. Now they're not drawn as mirroring. They're drawn because the backbone is the same. We know if we switch this to S and that to S, we get the mirror image. Go home tonight and do this in the mirror. Your mirror image will have the right leg sticking up and the left arm sticking up. Everything will be reversed. Okay? What's the relationship between these 2? These are also enantiomers. Yes. What's another another name we can give enantiomers, or if we want to call them? It's a pair of enantiomers, a DL pair. A pair of enantiomers is often referred to as a DL pair. Because if you have enantiomers, doesn't one rotate pp light to the left and one rotate pp light to the right? Okay? So that's that terminology. That's a DL pair. It's a pair of enantiomers. This here's a DL pair. Well, what's the relationship between these 2? Are these enantiomers to each other? No, the enantiomer of RR is SS. That's not SS. Well, hold on. Are they stereoisomers? Yeah, they have the same connectivity. Every one of the compounds on the board has the same basic name. 2-chloro-3-hydroxybutane. Everyone has that name. Yes, 1 and 2 are stereoisomers, but they're not enantiomers. So what are they?
Diastereomers.
Yes, these are diastereomers. Diastereomers is the other type of stereoisomer. Diastereomer is sort of a default category. Diastereomers are stereoisomers that are not mirror images. Now, enantiomers have the same physical properties, same density, same boiling point, same dipole moment, because they have the same exact projection of the groups, just mirrored. But these don't have the same projection of the groups. Because if the backbone is the same, both of these groups are coming forward, where here one's forward, one's back. Now, of course, this has free rotation, and you can rotate that, make that forward, but then this would not be the same backbone. These are not mirror images. We can do models, you can see they're not mirror images, but we know that because the mirror image of RR should be SS. That's not SS. Diastereomers. Diastereomers in the definition is given down, it says number 4, stereoisomers that are not mirror images, they have different physical properties. Bromination lab. You had 2 potential diastereomers that could be made. One had melting point in the low 100s, the other had melting point in the 200s. 100-degree difference of melting point. Enantiomers are very hard to separate because they do the same thing. They have the same solubility, so one's not going to crystallize and the other stay dissolved. They have the same boiling point, so how are you going to separate them by distillation? Very hard to separate. We'll talk about how you can separate it. Diastereomers are much easier to separate, unless you're just sort of unlucky and they happen to have very similar boiling points. But often diastereomers have very different boiling points or very different solubilities. But I also remind you of our stereochemistry outline table here. Isomers, well, 2 types of isomers. Stereoisomers, 2 types of those. Enantiomers, which are mirror images. Terminology, you can have like R and S or D and L. 2 different ways to describe an enantiomer. Diastereomers are not mirror images. What type of terminology would be used here? Cis, trans, erythro, trio. We're going to do erythro, trio. While I'm talking about it, what about cis-trans? Look at these 2 compounds. We've had them drawn before. What's the relationship between these 2? Well, this is cis, right? And this is trans. Okay. Well, here, what's the relationship? First off, are these isomers? Yeah, they have the same formula. Okay, are they constitutional or stereo? You name them, it's the same name. It's 1,2-dichloroethane. Both of them are 1,2-dichloroethane. They're stereoisomers. Okay, what type are they? Are they enantiomers? Well, first off, are they mirror images? No. The mirror image of this would not be that. If this was a mirror, let's do the mirror image of that. Wouldn't the mirror image of that be this? That was the mirror. Wouldn't you see that? Yeah. The mirror image of cis is cis. If you go home and stand up with your arm cis, not like this, look in the mirror, the projection will have its arms cis. If you go home and stand like this, and in the mirror you have something like this, let me know. Okay? Mirror image of cis is cis. These are not mirror images. So they're stereoisomers that are not mirror images. So what do you call them? Diastereomers. Diastereomers. Cis and trans are diastereomers. Okay? Now what is erythro and threo? We're going to see that here, because one of these can be called erythro and a threo, but let's do that. We first have to draw these in Fischer projection. Questions?
Would number 3 and 4 be diastereomers as well?
Where are you at?
The one we were just talking about, D.
Yeah, we can also say, yeah, these are diastereomers. The relationship between these would be diastereomers. Because that's SR, the enantiomer would be RS. Well, that ain't the enantiomer. But they are stereoisomers. So if they ain't enantiomers, then they're diastereomers. That's sort of a default category. So we got 2 DL pairs, and then the other relationships are diastereomeric. Let's draw this in a Fischer projection. I think I want to get rid of this. Fischer projection. Okay, we have 2 chiral carbons. We have 2 chiral carbons. We need 2 crosshairs. So we're going to have boom, boom, boom. 2 crosshairs. I want to get rid of this. I'm going to number the backbone since chlorine comes before hydroxy. 1, 2, 3, 4. That's nomenclature numbering. The 2 and 3 are our chiral carbons. Now, I'm going to put 4 here. 4, 3, 2, 1. I think that's going to be best for the beginning. That's going to be our backbone. And at 3 and 2, we're going to have the 2 substituents. But are they going to be on the left or the right? Now this on the end looks a little naked to me once we get it up there. These are methyls on the end, so I'm going to draw that there. All right. These are methyls on the end. You can draw CH3. What's on carbon 3? An OH and what else?
H.
And an H. Okay, an OH and an H. But which side is which?
OH is right.
Let's do that. Okay. This methyl, is it going forward or back? That's a Fischer projection. Top and bottom going back. Okay? So with the methyl going back, what side's the OH on? That's the question. Well, look at this with the methyl going back. Carbon 3, here's the methyl off of carbon 3. With it going back, we have to stand where? Over here. If we stand over here with our feet on the ground, and I look through there, here's carbon 3. Isn't the methyl going behind carbon 3 compared to my view? With the methyl going back, what side's the OH on? It's coming towards you guys. If I'm over here, that's the left. The OH is on the left. The H here is dashed. It's going behind the board. If I'm over here, because the methyl needs to be going back, the H is on the right. Okay? Now, let's look down here. Now carbon 2. This methyl is going back. That's implied. If I'm over here, I can bend my knees and just bend down. The methyl is coming towards me. So what do I need to do? Some books may tell you to rotate this. I don't. I would come over here and stand. Keep your feet on the ground. We'll talk about the ground. Because why is this the ground? Because 4, 3, 2, 1. Isn't methyl 1 closer to the ground? Methyl 1's closer to the ground. Methyl 4 is up in the air. Right? This is the ground. If I stand over here with my feet on the ground, methyl 1 going away, that's implied. With that going away, the chlorine is on my right, because it's coming towards you guys. Chlorine's on the right. The H is over here. There's that compound drawn in a Fischer projection. We need 2 crosshairs because we have 2 chiral carbons. Now, the enantiomer, which is number 4. Can you draw the enantiomer in the Fischer projection? Well, actually, you can just cheat. I'm going to cheat, and then we'll come back and we'll do practice here again. But if you want to draw the enantiomer of that, well, you can just draw it mirrored. You can have methyl, methyl. I mean, that's actually number 4 right there, 1. But then we draw OH here, H here, chlorine here, H here. Are those two Fischer projections mirroring each other? You see that they're mirroring? Yeah. This is this one. Because here's the methyl with the connector. If the methyl is going away, the OH is on my, it's going back, so it's on my right. With the methyl going away, the OH is on the right. Well, we cheated because we knew we could just draw the enantiomer of the mirror image of that. So there you go. Is this R and S? Well, we can confirm. This better be R and R if we're drawing this molecule. And that you can always check yourself. Is that the same molecule? Well, is it R? Okay, here. Oxygen is 1. Carbon with chlorine would be 2. Methyl would be 3. So it's counterclockwise, but the H is forward or back? On the side. It's hugging. The H is forward, so it's counterclockwise, but the H is forward, so what do? We switch it. It's R. Check, I got that right. Down here, is this R? Okay. Chlorine is 1. Carbon with O is 2. Methyl's 3. Counterclockwise, but the H is forward. So what is this? It's R. It's the same exact sterilizer. So we checked ourselves. I'll bet you a steak dinner that this is S and S. Because in the Fischer, if you just disconnect and put the OH here and the H here, that's like changing the projection. You check yourself, make sure those are S and S. Those are enantiomers. Okay, let's draw number 2 in a Fischer projection. Now you can sort of actually cheat again because you know that there's just going to be one change. But let's do it from fresh. We need 2 crosshairs. I'm putting this carbon at the top. So that's 4 and this is 1. We can draw the methyls there. Okay, with 4 going back, what side's the OH on? I stand over here. With 4 going away, what side's the OH on?
Left.
Coming towards you guys, on the left. But of course it is, because that configuration is the same as that one. But down here, carbon 1, we want it going away. That's what it implied here. So we need to come over here, feet on the ground. If I'm looking through here with carbon 1 going away, the chlorine is on my, it's going behind the wall, so that's my left. Chlorine's on the left with the methyl going away. The methyl going away, the chlorine is on the left. The H is over here. Those are methyls. You can draw them in. There's that one. And this one, I'll bet you a steak dinner, is RS. You can see that these two are not mirroring each other. A different configuration at the carbon with the chlorine.
So I'm not understanding, like, I understand how the first one is the which is conjugation, but isn't the chlorine going away? So
Chlorine's going behind the board. If I'm over here, why am I over here? Because we want to stand with the methyl going away compared to the carbon. The methyl's over here. So I'm over here. If the chlorine's going behind the board, it's on my left. Methyl going away, chlorine on the left. methyl going away, and that's, which is implied. The methyl going away, the chlorine's on the left. That's why I do it on the left.
Okay. So the second part is you get to look at it with the methyl going away.
This drawing here, this methyl's going away. The methyl going away, the chlorine's on the left.
Okay.
How do I know that? Because if I stand here with the methyl going away, chlorine's going behind the board, so it's on the left. If I'm over here, the methyl's not going away from me compared to the carbon. It's coming towards me. So you don't want to stand over here. You can also check yourself. I've seen some students who don't even do any of this. They just draw the Fischer and they say, hey, I know it's got to be RS, so they put it up here. For this to be R, the OH has to be on the left. They just draw it R. So you can do it a variety of ways, whatever works for you. Okay, well this one here, we can sort of cheat. Well, those are enantiomers, right? I mean, everything's reversed here, so that means the OH is on the right and the chlorine is on the right. You see how these two are mirroring? And indeed, this is SR. One power of the Fischer projection is you can see the mirroring a lot quicker and easier. See when we drew these, how you see they're mirroring? Here, it's more difficult to see the mirroring. So that's another power of the Fischer projection. It's really easier to look at and to assess. Okay, so there are the four. We got two DL pairs on the outside. This is the DL pair. The relationship between these two diastereomers. The diastereomers can have names, like cis-trans or erythro-trio. Here's some naming here. If your high priority groups, which are the chlorine and OH, are on opposite sides in the Fischer projection, it's called 3O. So this is 3O. How about this guy? Also 3O. Because the high priority groups are on opposite sides. We'll clarify this. Now look, these are mirror images. The mirror image of 3O is 3O. Just like the mirror image of cis is cis. Okay? So that DL pair is called the 3O. Well here the high priority groups are on the same side. This is called erythro. And of course this is erythro. Because the mirror image of erythro is erythro. But this is really a diastereomeric relationship because now these are diastereomers, right? And what can we call them? Well, this is called the 3O diastereomer. And that's called the erythro diastereomer. And of course, the 3O has a mirror image, and so does the erythro. So erythro and 3O are diastereomers, just like cis and trans are diastereomers. Now, why do you use it differently? Because you may be inclined to call this cis, because they look both bold. The reason you don't want to call it cis is because this has free rotation. If I rotated it, I could make these two look like trans. In fact, let's rotate that one bond. The methyl would then be like this. That would stay the same. And indeed, if we rotated, the chlorine would then be like this. And these are the same. Because if you do R and S, they're both RR. These are the same. So is it cis or is it trans? doesn't work here because of free rotation. That's why we use a rethrow in 3O. What it is 3O. And 3O means that in the Fischer projection, the groups are on opposite sides. Both cases, if you draw them in the Fischer, the high priority groups are on opposite sides. That's why this is called 3O, and 3O doesn't matter if you can rotate it. How do you remember 3O and a rethrow? Well, if you draw a capital T, you have on the horizontal points on both sides, like opposite sides. But if you draw a capital E, all your horizontals are on the same side. Okay? A rethrow, high priority groups are on the same side. But 3O, opposite sides. That's how I remember a rethrow 3. Now in E, with alkenes, E means opposite. Right? So Z is the same side. So the E's actually are different from alkenes versus this. Okay. So we have diastereomers. Questions about this? We'll move to the next compound, which has got 2 OHs. 4 stereoisomers. There are your 4. New terminology. Fischer projections with 2 different chiral carbons. Okay, you need to redraw. I'm going to just change the chlorine to an OH. Redraw the original 4, but with just OH here. Okay, we're looking at the second compound on the yellow page. How many chiral carbons in the second compound? 2. It's just like the compound above. It's 2 chiral carbons. So 2 to the 2 would be 4. We expect 4 stereoisomers. That would be max. There could be less. The configurations is the same because the OH is still high priority here, just like the chlorine was. So that's RR. This should be what? RS. SR and SS. They should all have the same configurations. Okay, Fischer projection, I'm going to leave it up there, maybe you redraw them. Fischer projection of this, again, if that's 4 and this is 1, with methyl 4 going away, the OH is on left. Methyl 1 going away, the OH is on the right. Okay, these are all the same. I'm just going to change this to OH. Just going to change that to OH. He's going to change this to OH. Let's get rid of this. Those should be the corresponding Fischer projections if you want to redraw those, or you can just put an OH sort of in parentheses beside your chlorine. Okay, how many different compounds on the board? How many different compounds on the board? What's this for? How many? One compound? What's the hesitation? How many, before we, with the chlorine, how many were on the board? Four. Well, how many are there now? Okay, well, let's see. Okay. Okay, this guy. What's the relationship between this one and the one on the far end? Yeah, that's a DL pair. Those are enantiomers. We'll confirm all this. What's the relationship between these two? By the way, this is a resonance arrow. I'm using it just to say, hey, what's the relationship between these two? Diastereomers, right? Well, they ain't mirror images. The mirror image of RR is SS. Those are diastereomers. What's the relationship between these two? Anybody? Enantiomers? You confident in that? No. These are the same. These two are the same. Same exact molecule. Same exact molecule. Are these mirror images? Yeah, they're mirror images. Everything's got a mirror image. Are they different or not? Here, you see how they're mirroring? Same or different? Well, how did we know that this was, how did we know that the mirror image of this was, are these are mirror images. Same or different? Same. Why are these the same? Because we have a plane of symmetry. We said if we can find the plane of symmetry, that the mirror image is the same. Do you see a plane of symmetry here? Difficult here. Look at the Fischer projection. Do you see a plane of symmetry? See how the top is the same as the bottom? Is it really? The OH, this OH is coming forward, correct? So is that one. They're both coming forward, but they're mirroring each other. If you can, does everybody see the plane of symmetry? Here it's much more difficult. Actually, let's build the molecule and then find it. Carbons. OHs will make blue like water. Zip, backbone. Zip, zip, zip. Forward. Uh-oh, that was going back. Well, that's what we want. There it is. There it is on the board. Do you see a plane of symmetry? Well, that's not. But hold on. What if we rotate that like that? Do you see a plane of symmetry? Yeah, cut right through here. Blue mirroring blue, black mirroring black. H is, okay? But look, or we could draw it in a Fischer projection because it's forward. Looks like it's cis. Well, that's trans. Remember? It's free rotation. There it is on the board. Fischer projection. If I'm putting, if this is the top carbon, with this going back, well, hold on, this is not going back. It's coming towards me. So I'll move over here. With the methyl going away, the OH is on my left. It's coming towards you. With the methyl going away, OH is on the left. Methyl going away, OH on the left. Down here, uh-oh, this methyl is coming forward. The methyl going away, the OH is on my left. That's how we got to that Fischer. It's much easier to see planes of symmetry in Fischer. Since it has a plane of symmetry, what does that tell us about the mirror image? Mirror image is the same. Now I can make a model of the mirror image, and it would look just like this. Okay? Does everybody trust that if you have a plane of symmetry, the mirror image is the same? Yes. So this is just one compound. Now, these on the external, are they aretho or threo? What is this? Threo. And the mirror image is threo. What do you want to call this guy? You could call it aretho because the higher priority groups are on the same side. But it's not called aretho. Instead, it's called what?
Meso.
It's called meso. Meso is a specialized type of aretho. And what does meso mean? Meso means that the mirror image is the same thing. A meso compound has an internal plane of symmetry, thus making the mirror image the same thing. This is one compound. So how many total on the board? 3. There's only 3 on the board. The 2 to the n, that's the maximum number. You can't have less if some of your compounds maybe are meso. What you have on the board is one DL pair and then a meso compound. Now, a little tricks here. If you didn't draw the Fischer, how can you tell that this is an internal plane of symmetry? Well, here's a little trick. Free information, okay? You can make a donation on your way out. Okay? We're saying that there's a mirror between the 2 chiral carbons. If this is mirroring each other, if that's R, and that's supposed to be the mirrored image over there, what's the mirror of R? S. Okay? See, that's R. If this is a mirror of that up there, the mirror should be S. How do you know that this is not a mirror plane? Because the mirror of R is not R. You see? Okay? Is that a mirror plane? No. OH is not mirroring OH. It's not a mirror plane. The compound has no mirror plane. Thus, the mirror image is different. It's the enantiomer. So that's a little trick. A meso compound is going to be like RS because the 2 halves are mirroring. Of course, you also have to have the same thing. OH, same connectivity. If that's an OH and that's chlorine, right? If that was chlorine, that's not a mirror image. I mean, that's not an internal mirror plane because obviously OH is not mirroring OH. But now that we have the same exact groups and we have mirrored configurations, so that's a little trick to recognizing meso. RR is not meso. Questions about that? Okay, diastereomers. Question down here with the structure drawn. How many chiral carbons does that drug contain? Actually, I want you to do that one for Monday. There's also questions on the daily question page. You should pretty much be able to do all those now on the daily question page. There's also questions in the white handout. Okay, various questions. Please try to answer them all, because on Monday we're going to finish everything up, see what type of questions there were. Okay. Let's look over in the white handout. Over here at the carbohydrates. In biochemistry, you'll study carbohydrates, and they will be shown in Fischer projections. Any questions about Meso? Any questions about the bromination lab report? Carbohydrates, drawn in Fischer projection. Your one carbon is more than one, but it's one chiral carbon. It's called glyceraldehyde. From there, you can start adding carbons and get larger carbohydrates until you eventually get up to like a glucose. But if you add one to there, you can get either erythrose or threose. Oh, this sounds familiar. In erythrose, the two OH groups are on the same side. It's erythrose. Where in threose, the OH groups are on opposite sides. And that's called threose. Okay? Well, that's where these terms came from. Because originally, this was called erythrose. But then people started saying, well, when high priority groups are on the same side, we'll call that compound erythrose, analogous to erythrose, and analogous to threose. Okay? What's the relationship between erythrose and threose? Well, look at the structure. What's the stereochemical relationship? They are stereoisomers. What's the relation? Are they mirror images? The mirror image of erythrose would be erythrose. OHs would be both here. They're diastereomers. They're diastereomers. What's the difference in the two molecules? Where? Is there any difference up top? Actually, yeah, the difference is up top. The bottom chiral carbon is the same. Actually, in every carbohydrate on this page, the bottom chiral carbon is the same. The OH is on the right. That's why every carbohydrate on this page is called D. Now, capital D is not the same as a little d. Little d means it rotates light to the left. Capital D is something different. Okay? The difference here is just right here. There's the difference. Now we need to introduce a new term. Let's look down here. There's glucose, which we're more familiar with, but allose and altrose. Let's look at these two. What's the difference? No difference here, here, or here. The difference is here. So the configuration has been switched. If you switch sides in the Fischer, that's analogous to switching from dash to bold. Okay? So what's the relationship between these two? Diastereomers. Why? Because the mirror image, everything would be switched. And going from here, only one thing has been switched. Those are diastereomers. And when you have diastereomers in which only one chiral carbon has been switched, those are called epimers. Epimers. Epimers are a type of diastereomer where only one has been switched. Ribose and arabinose are called C2 epimers. Because the only difference is right here, and that's the 2 carbon. That's 1, 2. At the 2 carbon, we have a switch in the stereochemistry. There's no switch here and here. So they're called C2 epimers. The change is at the C2 position. An epimer implies there's only one change. Over here, these two are C3 epimers. Because the only change is right there. Everything else is the same. They're diastereomers. Because the enantiomer of this, everything would be changed. Epimers. Okay, let's pretty much out of time. A couple things we need to cover on Monday. Separating enantiomers, resolution of enantiomers. Please look at that. This on the back is sort of a little miscellaneous. We may or may not cover it, but it's can other atoms be chiral other than carbon? What about nitrogen? Can it be chiral? That sort of addresses that. And again, there's lots of questions that are in handouts, including the daily questions. Please be looking for those questions. Maybe they're handwritten. Okay, for practice. And we'll do those on Monday. We'll also begin alkyne chemistry on Monday. I sent that handout by email several days ago. See some of you in lab this afternoon for polarimetry. Have a good day, guys.